Okay, folks, so I want to do a proof of the mean value theorem here. So, first thing I want you to do is I want you to copy down what the mean value theorem states. So I'll do that in a moment, but I want you to try to do what you can do from memory. So pause the video, write down what you think the mean value theorem says, and then we'll check back. So here we have our statement of the mean value theorem. Do not forget the conditions, right? It's the conditions that make it true. So we require f to be continuous on a closed bounded interval and differentiable on the interior. If that's the case, then we're guaranteed to find a c value so that the instantaneous rate of change at that c value equals the average rate of change over the entire interval. So the next thing I want to do is I want to look at this function that we explored in our pre-work. So here's our proof. This is our proof, folks, and it really is just an exploration of that function that we saw in our pre-work. So let's let h of x equal the function f of x minus f of b minus f of a all over b minus a times x minus a plus f of x. Oops, excuse me, plus f of a. So, folks, I don't know if it's entirely clear where this function comes from if you just look at it in a vacuum. But again, if you're curious, go back and rewatch the pre-work video about this function h of x, where we got to explore a lot of its properties. We actually looked at a graph there and saw how it was measuring the distance between the function and the equation of the secant line connecting the two endpoints. So I'll let you go back and look at that video. But what I'd like to now do is just look at some of the properties that now carry over. What do we know about h of x? Well, h of x is continuous on the interval ab. Why? Well, let's look at what h of x is comprised of. H of x is comprised of the function f of x and this line right here. Again, this may look a little bit messy, but really this is the line m times x minus a plus maybe just some b value, b there. Okay. Let me not use b because that's maybe a loaded word or loaded symbol. Let's just go ahead and say plus k or something like that. So this is just a linear function. As far as x is concerned, this is a linear function. So how do we envision h of x? We think of it as being the function f of x plus a line. Well, what do we know about f of x? F of x, well, because we're meeting the conditions of the mean value theorem, we know f of x is continuous on AB. And we know that any line is continuous on AB. Again, this left-hand side here is just a line. The left-hand part of this function is just a line, and so is their sum. That is, if this is a continuous function and this is a continuous function, if I add the two together, or I guess in this case I'm subtracting one from the other, but their combination is also a continuous function. Okay? What else can we say? Well, we can say that h of x is differentiable on the interior. Why? Well, f is differentiable on AB, and so is any line, and so is their sum. Okay, let's go through that again just to make sure. What do we know about f of x? We know f of x is differentiable on the interior. Why? Whoop, my computer's frozen. Why? Because we required it to be so for the condition of the mean value theorem. And what else is h of x comprised of? It's comprised of this line, but lines, of course, are about as differentiable as you get, okay, where the derivative is just their slope. And then we've seen before that if I take one differentiable function and subtract it from another differentiable function, the result is a new differentiable function. So we know that h of x basically inherits the same properties that f of x has, because the only difference between h of x and f of x is that we've added this linear component to it, this x minus a line here. Okay, great. So now let's go ahead and do some exploring with h of x. And we saw this before, but I want to go ahead and reiterate it. So if you're curious about why this is so, go back and watch the video. We'll give you a good physical interpretation why this is so. But let's go ahead and see what h of a is. H of a is f of a. So I'm replacing this, all these x's here with the a value. Right? So that's f of a minus bracket f of b minus f of a all over b minus a. And then I have, right here, I have a minus a plus f of a. I know that's a lot of a's floating around. Okay? But all I did was replace the x in h of x. So there's the x in h of x. I replaced those x's with the value a. And look what happens. Everything kind of collapses in on itself. We're left with f of a, and then we'd get minus, notice that we have a minus a, that gives us 0. And so this entire expression here, it just zeroes out. So we got 0 plus f of a. But look what happens here. We get f of a minus f of a. The result there is 0. Let's see what h of b is. H of b would be f of, so again, I'm going to go back to this, the description of the function here. Everywhere I see, I know I've got lots of a's and b's floating around, but everywhere I see an x in the description of the function, I'm going to replace it with a b. So there's h of b is equal to f of b minus bracket f of b minus f of a all over b minus a times b minus a plus f of a. Alphabet soup here, or at least AB soup here. But look, there's the b that I put in there from the function. I replaced x there with those b's. Great. And now look what happens. Okay? In this case, this again collapses in on itself, but a little bit differently. We get f of b. Notice here I could cancel out these two factors. Let's cancel, I guess, cancel them out. Boom. And we're left with then minus f of b. And then if I distribute this negative through, that gives me a plus f of a. And if I distribute this negative through to the second sign, we get minus f of a. And look what happens. We've got f of b minus f of b plus f of a minus f of a. And it again zeroes out. That's pretty interesting. Okay. So what we've just shown is that h is continuous on AB, differentiable on the interior, and h of a equals h of b. But now that Rolle's theorem that we learned in the pre-work applies. So if you go back and you look at your requirements for Rolle's theorem, we've just met all three of them. The function's got to be continuous on the closed bounded, differentiable on the interior, and there was this wacky component to Rolle's theorem that said the two endpoints had to agree with one another. Well, that isn't necessarily the case for the original function we were given, f of x. There's nothing that says that the endpoints have to be equal, but we created this new function h of x. And if you want to see more about h of x, go back and watch the pre-work video for it. And h of x does have the fact that the two endpoints equal each other. So by Rolle's theorem, there exists a c value in the interior so that, we're so close, so that h of c equals 0. Oh, excuse me, h prime of c equals 0. That is, Rolle's theorem said as long as you meet these conditions, with the heavy condition being that the two endpoints equal each other, there's no way to go from here to here in a continuous and differentiable manner without having at least some point where the derivative is 0. And that would be that c value that we could plug into the function. So we're going to take that c value. We know that h prime of c is equal to 0, but also, I'm sorry to be running out of room here, folks. If we take the derivative of h of x, let's go back to the original function, h of x, that we were working with, and let's take its derivative. So here's the function h of x. When we take its derivative, the derivative of h of x, h prime of x, will be f prime of x. And then this is a line here, folks. What's the derivative of a line? The derivative of a line is just its corresponding slope. So h's derivative, h prime of x, will just be f prime of x minus f of b minus f of a all over b minus a. Where did everything else go? Well, remember that this was essentially just a linear function. That this is just this slope times x. And what's the derivative of slope times x, or a constant times x? It's just that constant. Everything else, that's a constant term, that's a constant term. Everything else is a constant, and it dies off when we take its derivative. It becomes 0. So finally, let's put these two bits together, that we know h prime of c equals 0, and h prime of x equals this. So what would be h prime of c? H prime of c, if I replace the x's in here with a c, is f prime of c minus f of b minus f of a all over b minus a. Whew, I ran out of room. I guess we better put it back down here. But since we know that's 0, then we have that f prime of c minus f of b minus f of a all over b minus a, that must equal 0. And so finally, if I solve this for f prime of c, I get the mean value theorem. F prime of c equals f of b minus f of a all over b minus a. And there at long last, then, we have the mean value theorem. Okay. Folks, that's a tough proof, but it's amazing you've got all the tools you need for it. So if this was confusing, please rewatch this video a couple more times, go slowly through it, and then let me know what your questions are. Thanks for your patience, and I will see you next time.